What has been an excellent week, or excellent workshop and conference. And to start us off today, we've got Dmitry Chelkak from Zurich and the Russian Academy of Sciences, who's going to tell us about scaling limits of critical Ising correlation functions in planar domains. So, Dmitry.
Yeah, do you hear me? Well, thanks for coming this Friday morning of excellent week, and that's my first time in Cambridge, so I would like to thank organizers for bringing all us together to here. That's an excellent place. And for today, well, I'm going to speak about critical Ising correlations, and most of you probably already heard about that several talks even during this week. So for instance, we had an excellent talk by Clément Anglais, who is one of the main actors here, in all this business as well. And the general idea of my talk today is to omit all the technicalities and instead to give you a kind of an overview, what is known and what we do expect and what is, the global picture. So, and here is the list of co-authors, of guys involved. And the basic plan is to start first with a general introduction, what we expect. So what should be a structure of limits of some functions, some local fields defined on in discrete, on lattices. And the second part is what you probably, at least most part of you already heard, either here or somewhere else. That's about fermions, energy densities, spins. So the story started with a paper by Stanislav Smirnov in 2006, and then it was some development by the guys involved. And the very last part is stress energy tensor. This is a kind of a new material, and this is a project, still a bit ongoing, but more or less fixed, with Sasha Glassman, who is here, who is now in Geneva, and Stanislav Smirnov. So that's the plan. And I should also say that there is, the understanding of this very last object, stress energy tensor, there is another project by Clément and Stéphane Benoit, so somewhere here probably as well. That's not immediately clear what should be, a right definition of this guy. So maybe there is just no unique correct definition. So, but we will see how it goes. Okay, so just a very brief introduction. What is the Ising model? I'm not going to give you a definition because you already saw it several times. So basically, you have some lattice, or maybe planar graph, and there are spins which are either plus or minus sitting at vertices or at faces. I would prefer model on faces. And the lattice is, say, for today, either square grid or honeycomb grid. Or maybe, basically you can play games with other lattices as well, as we saw, for instance, in Beatrice's talk. So then, what is the configuration? Configuration is just spins plus or minus sitting at faces, as I said. And I would prefer to draw domain walls between those, which means that, given a domain, we have a number of contours or loops, of course nested, in this domain. And the probability of each particular configuration is just proportional to some parameter to the number of edges. And then you can tune this parameter to have an interesting behavior. If it's too small, then you see completely ordered phase. If it's too big, too large, then you see a complete disorder. But there is a critical point, which is on the square lattice, this guy. And on the honeycomb lattice, this is this guy. Those are tangents of some angles. So I think we saw those critical weights in Beatrice's talk already. Okay, so for the honeycomb grid, there is another name for the same model. It is called loop O1 model. just to mention. I mean, but just let us think about the Ising model. Okay, and what are the questions? So the basic question is as follows. So there are spins here, and we would like to understand what's going on in the limit when the mesh size goes to 0. So basically, we just ask what is the expectation of a given spin in the limit. And here there are, well, several setups, and the setup we work with is that we have a fixed geometric shape, omega, and then we discretize this geometric shape finer and finer, and so let it be called omega delta. So many of you attended the course by Clement, so this is exactly the setup he told about. And we ask what is the limit as mesh size vanishes. Basically, I'm going to have this blackboard for discrete stuff and this blackboard for continuous stuff. That's why I wrote it here. I mean, it's going to converge to something on the other blackboard. And well, as you probably know, basically, if you just ask this question, so for a fixed point inside, that answer is 0. So there is nothing non-trivial. The magnetization is 0 at criticality, which is a meaningful statement by itself, but nevertheless, the answer is trivial. So you should rescale somehow with some exponent. And this is the question. And as you probably know, what we expect should be conformally invariant or conformally covariant. And the other question, so this is just for the spin. The other question of the same sort is, okay, if I have an edge somewhere, I can just wonder about what is called energy density. And okay, if here there is an edge A, I just consider two nearby faces, denote them somehow, I don't know, A sharp, A flat, and think about the product of spins there. So let me use another color. What is energy density? Basically, this is just the product of spins. And then you ask the same question. And again, in this setup, the answer is trivial because what we see in the limit is just the infinite volume picture. So it's going to be a constant. You subtract this constant on the square lattice. This is this guy. On the honeycomb grid, this is 2/3. And then, okay, this is the object you are interested in. It vanishes in the limit. Again, you should rescale somehow. So this is the setup. And there are several remarks here. So, of course, there is something to do with boundary conditions. So boundary conditions for today, let them be just all pluses. It means that there are no interfaces attached to the boundary. You can also think about what is called Dobrushin boundary conditions, and they appeared in Hugo's talk, Hugo de Menil-Capin talk on Tuesday or maybe Wednesday. Okay, so some day of this week. You can think about free boundary conditions. You can mix them up. Let it be all pluses for today. And we are now at the stage where all those questions are more or less doable with any mix of Dobrushin free, of plus, minus, and free boundary conditions. Okay, and then the second remark is about techniques. So what are the techniques available? And basically, there are three things to mention. Well, in some sense, this is all about the same story, of course. So the first is more algebraic, anti-commuting variables, or maybe fields, like fermions. And the first instance they appeared, as far as I know, is a paper from 1960 by Hurst and Green. This is some formalism that allows you to compute things using those anti-commuting variables on the lattice. So Hurst and Green 60, and then it was some story, and the subject is still alive. So this is exactly an approach on which this Italian group, Mastropietra, Gilani, and Greenblatt, they were able to make a rigorous renormalization procedure for energy densities. Clément mentioned this in his talk at the very end. So there is a paper of, I think, 12 by Greenblatt, Gilani, and Mastropietra, where they analyze a model with not nearest neighbor interaction. So that seems to be quite promising. I mean, and everything that we can do is very fragile. So we are stuck with nearest neighbor interactions. And the second approach is reduction to dimers. So as I mentioned at the very beginning, so I'm just going to give you a more global picture of what is around. I mean, instead of going into technicalities. So, and reduction to dimers, it started more or less the same time, in 60s by Fisher, by Castellane, by Temperley. And then again, it was some story. And again, the subject is still alive, as we already heard from Beatrice's talk, for instance. So it was a paper, quite important paper by Julien Zubeda, who is here in 2011, I think, exact bosonization. By Julien in 11. And then there is further some business. So, and the third technique is just holomorphic functions on the lattice, discrete holomorphic functions. And there are, again, well, you can track it, you know, maybe just to 60s as well. And it was revived by Stas Smirnov and John Cardy in 2006. And this is basically the approach we use. So, as I said, at least up to some extent, this is all about the same. And I'm going to show you some instances of that. Maybe it's the last one slightly better fits the setup of bounded domains. But say in the full plane, you can use whatever you wish, and maybe even those reductions to anti-commuting fields are better. Okay, so this is just some comments about what are the techniques, and we are here. And yet another comment about domains. It's wrong to be simply connected. It's not necessarily the case. I mean, we can handle multiply connected domains as well, more or less by the same means. It is slightly more trickier with boundary conditions, but just believe us, it's doable. And some of the papers are actually written in more general setup. Okay, so what do we expect on the other blackboards? I mean, on the continuous side. On the continuous side, we expect, just for the first question, what any book in conformal field theory says us. It says us that it should be, for the first question, it should be the function, which I'm going to denote this way. So this is just a funny notation for a function in a in a planar domain omega of a single point. And okay, we expect that it behaves nicely under conformal maps, which in this particular case means, okay, here is domain. If I apply a conformal map, phi to something else, whatever, that would be phi omega without brackets, I'm going to save place. And there is a point here, phi w without brackets as well, and phi is not a field, sorry for that. Phi for this talk is a conformal map, always. So then what we have is the same up to some factor that depends, which depends on derivative. So we call it a conformal covariance. And if you, well, fix this rule, then basically your function is unique up to a universal constant. Just because, okay, in a given domain, you still can vary your point. There are some, there are some conformal maps. So basically, okay, you know what this function is in a disk, say, up to a constant, and then you transmit the information to everything else. And for the energy density, again, what you expect is like that. Oh, just one. And this is more or less a trivial observation, though quite important, is that if we would like to fit those two pictures, I mean, if we would like to have a statement of this sort, that those discrete guys converge to continuum ones, then the exponents here should be exactly the same. Otherwise, this is just inconsistent with scalings. You think about the same domain, twice enlarged, and okay, if the grid is twice enlarged, you have exactly the same quantity as you had, and if you subdivide, you have something else. I mean, just consistency with scalings say you that, okay, it should be the same. But of course, what is in the right is much more than scalings themselves. Okay, but then you can also wonder what are, I mean, so here there are two particular examples of what we call local fields, local combinations of spins. You can wonder about something else, like consider 4 nearby spins and think, okay, here let it be whatever, around some vertex, something like that. And think about the field which is something of that sort. What I'm going to mimic is a contour integration around this vertex. Then, basically what you expect is that still there is a convergence of expectation of this guy. Well, to something that most probably should be just a derivative of this function, a complex derivative of this function. So it should be some other objects like, okay, let me move it down, like derivatives of those functions. And we are going to adopt physics notation, so I'm going just to say, just to write it down in this way, just with the derivative inside. Okay, is it clear what I mean? I mean, if we believe the first convergence is nice, I mean, it holds not only for the function itself, but also for a kind of derivatives, then it should be also some objects of that sort on the right. And of course you can imagine, and it should be some rescaling here, and of course you can imagine many other combinations of spins here, and so you expect that there are many objects on the right. And let me also, well, keep some information, about covariances. Oh, it's thanks, many thanks. That's d sigma. I just put it inside. Well, and I'm going to say that this is another field, if you wish, that presents in this series. Thanks for saying sorry. And so what happens with covariances? So basically if we start with this covariance rule and rewrite it with two 1/16ths, then this is an easy exercise to check what should be the covariance of here. You differentiate here, you differentiate there, blah, blah, blah. And what you arrive at is the following. So if you think about logarithmic derivatives, say, then the answer is, okay, just another one, I mean, another multiplication by the derivative, but there is some additional term as well, which is in this case 1/16 over that guy. So this is just an easy exercise, and 1/16 is exactly this 1/16, and because our field is real, so it should be 1/8 over 2. I mean, there is just no other choice. Okay, so what you see is that, okay, this guy is somehow more involved than the very first one. And in the CFT language, the first is called the primary field, and all others, well, they're non-primary. And then you can imagine that, okay, you can take other derivatives, say d bar here, or d squared, or something like that, but that's not it. I mean, there are many more fields. And what is the construction? And again, it's already, well, we already had a talk by Julien with Virasoro algebra inside. So basically, just a quick reminder of this story is that here there is an action of Virasoro algebra. So, which means that there is a series of generators. They satisfy some commutation relations. Let me save time. And actually, there are two series of generators. One corresponds to conformal sector, the other to anticonformal. I mean, say L minus 1 is just D, and there is another one which is D bar. And well, basically, the story is that then there is Virasoro algebra. There are primary fields. Which are sigma, epsilon, and that's not it. There is a third one, which is just trivial, just 1. And then there are all the descendants of those. Which means you can apply all the generators to those guys, and you have something. So, like L minus 1 sigma is just the sigma, etc. But there is a very highly non-trivial algebraic structure. And to make some link with what I'm going to talk about, so one way of thinking about all that is the following. So in particular, there is a field which is called stress energy tensor, which is a holomorphic field. So it means that if you consider, say, single point correlation function, we expect it to be holomorphic function. It should be holomorphic function. So, which is, by the way, just some descendant of identity. That's why I insisted it should be another primary field. And all the generators are just Fourier modes of those. And to make it, well, more precise, if you just would like to act, say, on whatever sigma w, whatever sigma w1, etc., or maybe there are some other fields here, doesn't matter. So the recipe is that you just integrate over a big contour this correlation function. Z minus Wn plus 1 dz, and it should be 1. So basically it says you that there is a kind of a master guy in this structure that says you what the action of all the algebra is. And one of the questions, for instance, is if we can construct a reasonable discrete analog of this guy, if we can have, you know, exactly the same picture in discrete. And there are also some important formulae that I'm going to write down on this blackboard, just to be there. And they somehow describe what goes on when you collapse points. And well, you ask, what is the behavior of this guy? Just think about a correlation of those two fields. What is the behavior of this guy when z tends to w? And then the answer is that it should be, it is an analytic function in z, so it should have some Laurent expansion, and this Laurent expansion is as follows. Smooth terms, and this 1 over 16 is exactly that 1 over 16. The same holds for energy, and say, well, is it still visible what let me save place. The same holds for energy with 1/2 here, and if you collapse 2 points and consider this correlation, then there is an important parameter that appears, which is called the central charge of the theory. And also you can wonder what is the conformal covariance of T, of the field T. I mean, what happens with this correlation function when you apply conformal maps? And the answer is that it behaves like a Schwarzschild form. So T, well, I would like to write it down just to save some time. If you know what the Schwarzschild forms are, well, you are in business. If you don't, never mind. Well, some behavior of the same sort. It is multiplied by phi squared, and then there is some object added, which is called Schwarzschild derivative. So, and if you just think about what's written on the blackboard for a minute, so you can easily extract, say, from here and here, what is the action of L naught on sigma. It would give you exactly this coefficient, 1 over 16. So this is an eigenvector in the theory. And the action of L minus 1 is exactly this one. So this is the structure that we expect in the limit. And the question is, okay, which part of all this story can be actually justified? I mean, from the point of view of mathematicians. So we have a very nice description coming from, say, theoretical physics, and the question is which part can be actually proven. And the reasonable conjecture, well, the reasonable expectation is that in each combination of spins on the left, a local combination, being properly rescaled like this, has a limit which is one of those fields, and you can think about multi-point correlations if you wish. And other way around, all those guys, they indeed appear as limits of some local field. So it is expected to be very close pictures, discrete and in continuum. Okay? So this is the end of introduction, and the plan is that then I briefly remind you what you, up to some extent, already heard about fermions, energy densities, spins, etc. Are there any questions so far? Okay, if no, then there is a main object in the whole story. I mean, how we can prove this statement. So say this and that, those are theorems. And for primary fields, for spin and energy densities, we can also handle multiple point correlations. I mean, everything is already well, is already in place. So, and the main tool for all that is what is called fermionic observable. And this is purely combinatorial. So here is the definition that already, say, appeared, I think, in talk by Antti-Kemppainen. So plane with a finite domain, you just introduce a function, which is a function of an oriented mid-edge, which I'm going to call the source, and some edge inside. And the formal definition is here. What you do is you compute a guy like a partition function of the model, but with some funny complex factor. And just to make another link, it already appeared also in talk by Hugo in more general setup in FK model, where it was called parafermionic observable, so it was another factor here. Okay, here is the guy. And what is important about this guy is that it is discrete holomorphic. So if you never heard about this, it just satisfies some local relations that you can interpret as discrete Cauchy-Riemann equations. And moreover, it satisfies some boundary conditions. Well, boundary conditions, well, those are neither Dirichlet nor Neumann. Basically, they say you what is the complex argument of this quantity at the boundary. Not going to bother you with explicit things in discrete. And what is the philosophy here, which is basically due to Stanislav Smirnov? The philosophy is there is this guy is completely determined by this boundary value problem. We can try to ask ourselves what is the continuum limit, because it solves some boundary value problem in discrete, so hopefully we are able to prove convergence of solutions. And then what we should do is try to extract information from this boundary value problem to extract something meaningful. And in this particular setup, when I started inside, well, local values near the source. And here there is a piece of notation, this eta. This eta is a square root of the orientation of this edge. Okay, just something, you know, something to do with the orientation of this edge. Then local values near A, they give us some information about, in this particular case, energy density. And this is the content of basically PhD thesis by Clément from 2010. So they have a paper with Smirnov, and then in his PhD thesis, it's extended for multi-point correlations. Okay, and then the general story, well, the general philosophy is that, okay, we can ask ourselves what is the continuum limit of this guy. And in continuum, again, we have some boundary value problem. So in continuum, being properly rescaled, well, this is the theorem, what I'm actually writing. It converges to some function. And what's that? This holomorphic in Z. It satisfies boundary conditions.
What is eta again?
And ether is the same ether as we had here. So this is a complex number of modulus 1. And it encodes the orientation of this edge. This is the square root of this vector. Well, okay, so this is some parameter, some fixed parameter. This function is going to depend on this parameter. And well, we have this expansion ether over Z minus A plus etc. near A. So this is just a simple boundary value problem in continuum. And a number of remarks is that first, the solution to this.
What was under the square root?
This is the normal vector to the outer normal vector to the boundary. That's some boundary conditions. I'm not going to waste much time on that. Well, it says that at the point on the boundary, well, either this is purely real or has another prescribed argument. And remarks is that it's pretty easy to see that the solution to this boundary value problem is unique. Second, it's pretty easy to write down what is the covariance rule. I mean, how it behaves under conformal maps. And the recipe is as follows. So first, it should be holomorphic, and it should satisfy boundary conditions. Basically, the only way you can cook up such an object is to multiply by this derivative 1/2 to keep the boundary conditions. Then you're worrying about what happened here, and you immediately see you should multiply by another square root of derivative, but it should be real because this boundary condition is real. And so what you get is a function with some other eta, and eta prime, okay, it somehow depends. I'm not sure I can write it down properly, like that, on eta. What I'm saying is that you just cook up an object, and then you check this object also solves the same boundary value problem. As you know, the solution is unique. You're done. And third remark is that basically, starting from this uniqueness, that's also quite easy to see that you should have a decomposition of the following sort. It should be either by some function of AZ plus eta bar, another function of AZ, and this is dagger. So it should be somehow real linear in eta. And then the covariance rule for those guys is actually even simpler, so there is no eta anymore. And the covariance rules are okay. This is just multiplied by two derivatives. And if there is a dagger, then if there is a dagger here, then it should be complex conjugate. So basically, in physics terminology, what you have is that this guy is what you would denote by a product of two fermions, and this guy is what you would denote by this. Yeah? Yeah, thanks. It should be fine. So, and then you can reinterpret what I said about that all that approaches are all the same up to some extent. So basically, the most important thing in this rediscovery of observables by Stas was that a particular combination of those two can be treated as a solution to boundary value problem. I mean, so what we have is a boundary value problem for a combination of those, not for a single one. Okay, and then the very last remark, which is number 4, but the most important one, is that basically, as I told you here, local values has something to do with with the energy density. And well, how is it encoded in the continuum? And in the continuum, it is encoded just in the next term. So you just define this quantity. So we don't know a priori what this quantity is. So you just say, OK, I solved this boundary value problem. It gives me a function. It is properly defined. And then I denote this sign to be the next coefficient.
Does it look like symmetrical between eta and eta bar in the formalism number 3? Looks like symmetrical, like psi, psi. So it was psi bar psi or psi bar psi?
No, that's psi bar psi. So that's not conjugate. Yeah, exactly. I mean, so yeah, that's how it's written on the blackboard. So basically, this function is anti-symmetric in variables. If you interchange, this is just minus. And this guy, maybe it's better to put another I here, well, to be precise, because when you swap them, it just conjugates. This is true. Okay, but then here, I mean, all the ingredients are already in place. So basically how the proof of the second statement works, and this is due to Clement, is that, okay, we encode something in discrete. We have those objects encoded as solutions to boundary value problem. Then we prove convergence of solutions, and then we extract the information back. Well, some work is needed to be done. I mean, there are some technicalities due to boundary conditions, due to analysis near singularities. Nevertheless, it can be done. Okay? Are there any questions so far? Then there are two more remarks before I go to stress energy tensor briefly in last quarter an hour. So the first remark is that two more remarks. Maybe I just say it in words. One can wonder about multiple point correlations of energies. And this is due to so-called Pfaffian formulae. So you might know that there is some Pfaffian formalism for fermions in continuum field theory, in conformal field theory. Anyway, so you consider, basically in discrete, you consider the same pictures with many sources, and there are some identities in discrete that allows you to compute those multi-point observables. So this is again an old story. And second, well, how to deal with spins. Well, how to handle spins. And to handle spins, basically, well, what you do, you consider the same objects, but just imagine you are interested, in addition to some energy here, to the value of the spin here. And you try to invent something combinatorial that counts, that takes the spin into account. And then what is the value of the spin? Basically, this is the number of loops surrounding this guy. So you are trying to multiply this object by -1 to the number of non-trivial loops, say surrounding a given point here. Or maybe let it better be here. And try to play with this object. Try to ask yourself if it is discrete holomorphic or not. But if you leave it as it is, then there is a problem, because say on this picture, you don't know actually if it is surrounded by a loop or this loop is a part of an interface. So there is this slight ambiguity, I mean, how to define loops. And then what you arrive at the end, and what already Clement told about, is that you should consider double covers. And here you should multiply by another ±1, depending on if you passed around this point and entered the other sheet or not. I mean, I'm not going to to go into details just to save time, and anyway, that's Friday morning. But the overall picture is that you basically do the same, but with the functions defined on double covers with additional property, with additional symmetry between sheets. Like that, it differs only by the sheet, by this very last factor on two covers, and basically you play the same games. So you just consider, other boundary value problems here, and you encode your information through the solution to this boundary value problem. In particular, so just to handle a single spin, by some reason, Clement promised you I'm going to speak about that, and I was not going. So I mean, what is the source of this 1/8 or 1/16, how it appears? So basically, well, it appears in the following way. So just let us see this on the example of energy density. So as I said, there is a very simple covariance of the function f eta. It's written down here. And you can do an easy exercise in Taylor expansions and ask yourself, what is the rule to rephrase this coefficient in the new domain? And basically what you arrive at is exactly the covariance of epsilon. You can imagine the same things happens with spins. This is more complicated actually, so the things are on the carpet now because the spin field is not something expressible in terms of fermions immediately. So that's more complicated. But let me just save time and do not speak about this. Instead, presenting what we have about stress energy tensor right now. So the general philosophy here, yet again, is that we encode information through solutions to some discrete boundary value problem. Then there is a piece of work, maybe tens of pages, to prove convergence. That's non-trivial. And then, well, we extract the information back. Well, the information typically is written as some coefficients in those expansions, and we extract it back to discrete. You can imagine some analysis near singularities, and as far as I understand, Clement gave an example for spins in his course. So if you attended 2 previous weeks, well, you have some impression how it works. Okay, and now I pass to the stress energy tensor, which is a kind of a new material. And I should delete more space. Let me do it here. And while I'm erasing, just switch your mind to the honeycomb lattice. Okay, right now we are on the honeycomb grid, and this seems to be a bit important. And okay, what is the idea? Besides of all the algebra, the stress energy tensor should have something, well, with geometry, with the response of our system to infinitesimal deformations. So okay, if we are on the honeycomb grid, so if we are thinking about the Ising model here, then basically there is an equivalent way to proceed. And this equivalent way is as follows. You just split everything into triangles and then say, okay, there are 2 options. The first is that in the given triangle we just have nothing, and then it gives us the weight 1. And the second is that we have a piece of arcs, and it gives us the critical weight. Okay? This is just an equivalent reformulation. But then you can play more general things. You can say, okay, instead of just gluing triangles, I consider some discrete Riemann surface glued from triangles. This is the critical value. Glued from triangles and some rhombi. And for each rhombus, you just say, okay, there is a number of variants of what to do. It can be either nothing, then this is 1, or it may be like this, and this is, well, some x1. This may be like that. This is x2. And there are 3 more variants, which are this and that. T, W2. And all the weights, they depend on the angle. Okay, so this is, you can play a model on a more general graphs if you wish, but not only planar graphs, just Riemann surfaces. And the message here is that there are weights, there are some special weights depending on the angle, such that the following identities hold. So the first is that this should be, oops, I misused the colors. That's yellow. The first is that if you just glue 2 triangles together, 2 equilateral triangles together, this is the same. Basically, it says W2 is 0, and those guys are x squared, and this is x. The second is Young-Baxter. You can reglue things through rhombi if the picture is planar. And also there is a third one here that basically says you something like that, or maybe up to constant. But if there is a triangle and 2 rhombi, then you can again reglue your Riemann surface. The only message here, I'm not going to write down, of course, what is the explicit formula. The only message is that there are very special weights. And then there is a natural construction of a natural candidate for the stress energy tensor. What is that? Just imagine that we had a completely planar grid, and then we decided to modify it in a non-planar way, infinitesimally, just by gluing inside a very thin rhombus here. So this is not planar anymore. And in some sense, this is exactly what the stress energy tensor should do. It modifies the conformal metric locally. So just remind the talk by Julien. And then you ask yourself, okay, what is the effect of this transformation? How does this affect all the correlation functions on the original grid? Or maybe you can do something like that, just joining 2 nearby triangles and tilting slightly, say, this rhombus. And again, you're modifying the metric a bit. Okay, so you ask yourself, what is the response to those infinitesimal deformations? So, of the partition function, or maybe the partition function weighted by some spins or energies or something like that, to infinitesimal deformations. So this, what should happen in continuum, and what is on the blackboard is just a particular way of interpreting this in discrete. And the question is, of course, if you are able to compute what's going on. And well, let me just explain. The answer is yes. We are able to compute those guys in the Ising model, and we are able to compute those mixed correlation functions as well. and they indeed satisfy all the algebra which is on the right blackboard. So somehow we pretend that this is indeed the right object. So, and to give you a clue, I mean, how you do so, basically, how to compute. Basically, you just ask yourself, okay, can I write down pictorially what's going on? I mean, if I just think about the total partition function, what's going on when I add a small rhombus, how this changes. And you immediately see that basically the result is that you have more pictures first, because now you allow yourself pictures of this sort. Here there is an infinitesimal rhombus, so they could be connected along this thing one. That sort. And also you have some additional weights for pictures like that. And maybe if there are two loops as well. But the message is that anyway, you can easily write down the expression of this guy in terms of the original model and in terms basically of the very original observable I started with, when there is a single interface running from somewhere inside to some another point. Yeah. Yeah, well, basically here there are some coefficients, well, I'm slightly in a rush, that are derivatives of those weights. I mean, I'm just, well, what is under carpet is that you should differentiate with respect to the small parameter. And the additional weights and pictures here, well, they come from this differentiation. And the relative weights are more or less derivatives of x1, x2, etc. You can just write, you can just, you know, say, okay, I consider those weights, but it's a bit artificial. What I'm... Yeah, there are special functions of theta. And then you differentiate those at pi over 3, and it gives you some coefficients. And you are able to handle all that. And so what is the output? I should finish in 2-3 minutes. So the output of all this construction is that we have a local field. I mean, it can be written down explicitly in terms of spins, if you wish. That has a geometric origin of that sort. And that actually converges to, I mean, to T. And here, well, I should be careful. So what is true is that it converges, and if you consider correlations with primary fields, they converge as well. I mean, so we checked for sigma, for epsilon, for TT. You can do multiple correlations as well. That's not a big issue. But then there is a kind of a problem. Well, what I said to you is that, okay, everything is as nice as you can wish, right? But actually there is some problem. The problem is that we do not have a discrete holomorphic field on the lattice. I mean, there is some object, and we are able to compute its limit, but it doesn't satisfy the full set of relations. In particular, it prevents you from defining those generators of Virasoro in the way it's kept on the blackboard, because it somehow implicitly assumes that the integral, the contour integral, does not depend on the contour. So, okay, and now, well, now the very last comment is, well, just to summarize. First, we have some natural candidate, and it just has some geometric origin. Second, there are some convergence results for the object itself and for correlations with primary fields. Third, okay, it's not holomorphic in discrete. And just to finish, I would like to say that originally we started this project not to computing something for the Ising model, but to try to get results for other ON models. You should have a general impression that that's very important to have some objects in discrete which are holomorphic, which can be analyzed. And then you can do the same construction for the ON model. So we somehow pretend that there is also a natural stress energy tensor in the ON model that comes as an output of all that. So it's not restricted to Ising itself. But the problem is that it satisfies some local relations that I didn't write, but it's not fully determined by them. And this could remind you a picture with paraharmonic observables, say, in ON model. And we do not have at the moment a good recipe. I mean, if we can handle this or not. We were more optimistic 1 year ago. Well, still there is some optimism, but a bit restricted. Nevertheless, this is just the state of art at the moment. So thank you for your attention.
Any questions?
It's very naive, but is it obvious why in the continuum the stress energy tensor does correspond to this local modification?
That's another part of the story. I mean, so as I presented it, this is just an algebra, right? But you can remind, say, talk by Julien with those infinitesimal. So you remember, just cut a disk and then twist a bit. And if you think about that, so that's more like what we are doing here. So you might also think about, cutting a disk and replacing it by a small ellipse. By a slightly tilt ellipse. So this is exactly what stress energy is supposed to do.
Any others? Okay, let's thank the speaker once again, and we will resume in 5 minutes at 7 minutes past.